Okay, how do we measure reactive components in a bridge?
A reactive component, first of all, why in a bridge?
That's just the question they asked Patrick last in his state's exam. So
Okay, so
how do you measure the inductance of an inductor?
well, there are different methods to measure the inductance. The first thing that it came to my mind is a basic circuit, which is used, in fact, in some chips. I think by Texas Instruments. I'm not sure 100%. Where typically you buy the chip, they tell you connect the impedance, the inductance there, and the output. They directly convert it to digital code. So the only thing you have to do is connect the inductance there, and they do all this kind of black magic, and you just connect some data and clock, and you get out the data.
Okay.
But how does it work inside? Basically, you remember inverting amplifier. Typically, you have resistance 1, resistance 2, input voltage, and the output voltage is negative R1 divided by R2 times the input voltage, okay? This applies in DC, it applies in AC, so if this becomes a vector, so if you are using AC, it means that this is not a DC voltage but an AC voltage, and this you have the phasor, not the vector, the phasor of the voltage. In this case, we have resistance which are real, and therefore they just have a real component. It happens, it works, even if these are not resistances but impedances, okay? So the circuit works in the very same way if here you have Z2 and here you have Z1, okay? And so instead of having R1 and R2, you have Z1 and Z2, okay? And again, in this case, we are considering impedances, so they are phasors because they can have real and imaginary part, okay?
Yeah.
So let's say that we want to measure an impedance. How do you do? Well, very simple. The impedance Z2 will be simply a resistance, R2, okay? And the impedance Z1 will be R1 plus J omega L1, okay? We put there also some resistance because typically if you have an inductance, you have some coil, something like that with some ferromagnetic core, or even just not ferromagnetic core, could be just a coil by itself, which has an inductance. So you have some non-negligible resistance. You have to take it into account. Okay, so what you have to do is to plug these values into the equations. We have the voltage output, which is negative. Z1 is R1 plus J omega L1, and Z2 is R2, okay? Times input voltage. Okay? Now, what happens if we want the inductance, or if you want the resistance R1? So let's say this is our unknown. Okay? Well, you have R1 plus J omega L1 is equal to, this goes up, so V out divided by V in
Times R2.
Times R2, and then there is a negative somewhere, okay? Correct?
Yeah.
Yeah.
So now we minus R1.
Wait a second. Okay. Now,
oh no, we don't know R1.
now we don't know R1, but it doesn't matter because this is. Oh, I forgot. These are vectors. Okay, they are complex numbers because they are phasors.
Yeah.
And so what you have to do here is you have a complex equation, okay? Complex equation means that you have two scalar equations.
Yeah.
Correct? Because if you have a real number here, alpha plus j beta equal gamma plus j eta, something like that. If this equation is true, two complex numbers are equal, it must be simultaneously that alpha must be equal to gamma and beta must be equal to eta. Okay.
Yes.
Both must be true in order to have satisfy this equation. Okay. And here's the same. So we have a complex equation.
On this.
We have a complex equation, which means that we have two scalar equations. So the real part of this equation must be equal to the real part of this equation. So R1 is equal to the real part of V out divided by V in times R2, and L1 is equal to the imaginary part of
-1.
the same thing divided by omega. Now J because it's
that goes in the
this
imaginary
is the imaginary part, okay?
Yeah.
So
that's the
because there we said that beta is equal to gamma. So
yes.
So this is our imaginary part, and we have to take the inductance equal. So omega L is equal to the imaginary part of that equation, and that's it. So what you typically do is to, well, the omega is a, you know it, because here you will, V in will be some AC voltage, you know the value, so you generate it. You know the value of the frequency. You know this resistance, okay? So now we have here just, let's say that we have okay. So here at the input we have a resistance, which is, we call it R2, and here R1, okay? So you know the value of this resistance because you put it there. You know the value of this voltage, you read the output, and you get back by the real and imaginary part of this output voltage these two components. So typically, if you are interested in the inductance, you will calculate the imaginary part of the voltage. Here you have to make some decision. Real and imaginary part, in this case, when you want to measure the real and imaginary part of the voltage, you have always to refer to watt, okay? Because if you have a sine wave, let's say that this is a sine wave, okay? This is V1, let's say. If you have a sine wave which starts in 0, this corresponds to this is the imaginary axis, and this is the real axis. It means that the vector is here, right? This corresponds to a voltage, which is because the value in 0 corresponds to the value on the imaginary axis of the phasor. Okay?
Okay.
Confused? Okay.
Let's carry on.
No, tell me.
I need to see where we're going.
Okay, so this is the phasor. If the time doesn't start there, but it starts, so time equal to 0 is here. If the time starts here,
then it's purely imaginary.
Then it will be imaginary, okay? Now, there is not such a thing like a time 0. When you have a voltage, you have a voltage which changes time.
Yes.
It depends where you start to count the time. If you start to count from the creation of the Earth, it's 5 billion years ago, or maybe 2,500 years ago, according to some crazy people. But generally speaking, there is not a time zero. It's your choice. Okay, you have to decide that then this point is time zero. Okay, so the real imaginary part of the voltage is just a convention. Okay.
Okay.
So what you have to decide one moment. Okay. So if your moment is that V1 is 0, so that V1 is real, it means that you decided that
Yeah.
you decide that the time is 0 when V crosses
0.
0, okay? And that's your choice. Then V1 becomes real.
Well, V1 is now like your 0 reference, let's say, or your real reference.
It's a phase reference, okay?
Yeah.
It's your phase reference. So V1 decides that the time is 0 when it crosses 0. So V1 as the phase of V1 is 0. So we define we decided, it's our choice, that where we have V1, then the phase is 0, okay? Fine. Then, whatever other voltage has a phase with the respect of V1.
Yes.
So
we plot V out.
Whatever is V2, according to the load, it could be capacitive or
Inductive.
okay? Then they will have a phase, and therefore a real and imaginary part, which will be referred to V1. So in our equation, we decide that V1 is going to be real, okay? Or V1, in this case, I say V.
Yeah.
Okay, so the input voltage will be real. And then we have to measure the real and imaginary part of V out, okay? Which is something that you can do in different ways. One of which is to use a synchronous demodulator.
Yeah.
You remember how it works? So let's say that this is the voltage that we want to measure the real and imaginary part of. And basically what we do, let's say this is V, whatever is the V that we want to V out. So this is the output voltage
yes.
of the bridge.
Yes.
And simply what we do is to connect the output to a switch, an inverter, I don't know how to call it, which can either pass to the output the voltage unchanged, or give me a name for this one. V prime.
I'll say V out prime. It's a V prime.
Prime, okay.
V prime.
We are not sponsored by Amazon.
Yet.
Okay. Oh, actually, yesterday there was a competition by the students here that they won, yeah.
Oh,
very prestigious. $500,000 they won.
Really?
Yeah, it's a reserve. They didn't win them for themselves.
Yeah, the uni got
it. They got some research grants.
Oh, wow.
It's a pity because otherwise they were for like $100,000 per person.
Oh, that would be so nice to be a part of something like that.
Okay,
so double. That's going to be inverted, so it can't be V prime.
No, it's still V prime, which is negative V out. Okay, here is equal to V out. In this case,
yes,
the V prime is equal to V out. Here, V out is equal to negative V prime is equal to negative V out. Okay, who decides if the polarity is crossed or straight? We need some signal. So here we will have a control signal which decides
when it's inverted or not.
Okay. So our control signal is this one.
Oh, okay, yeah.
And let's decide that when it's 1, it's equal. This is position number 1, and this is position number 2, okay?
Okay.
Or 0, sorry. Okay, when it's 1, it's straight, and when it's 0, it's flipped. And then we apply what we've seen here. So here we have...
this will rectify it.
in this case, it's a rectifier, but it's a controlled, phase-controlled rectifier.
Yes,
which can be used for to demodulate.
I remember.
Okay? Okay, so then you take a low-pass filter and you get the average, okay? Now, if this control voltage keeps the same, this control voltage comes from the input voltage, okay? You can take the input voltage and you can square it. You can square it using an operation amplifier, okay? Comparator,
Yeah.
and simply you can flip with the same frequency. Well, you know that the output is going to have the same frequency of the input. In that
yes, that will never change.
If you have 1 kilohertz at the input, there is no reason whatsoever why the output should have a different frequency.
Well,
there could be some noise.
It could become 0. Like if the frequency is high enough, the inductor will open up. And it can get to a point where it's completely open and there's no frequency, there's no signal coming out.
Okay, so yes, okay. If there is some signal in the output, let's say, of course, then you would say, okay, let's say that I have
but that will be very
infinite
large
impedance in the feedback. So
yeah.
Let's say if I have some signal in the feedback, okay.
But generally speaking, the frequency will not change.
No, there is no reason why. I mean, of course, there will be some DC component because of the non-idealities of the operation amplifier. So you have some DC bias and so on. So there will be some DC component. There will be some noise coming maybe from the power supply of the operation amplifier. But generally speaking, if you have 1 kilohertz in the input, you get 1 kilohertz in the output.
Yeah.
Now, fine. So this is V prime, and this flipped, and there you get this value here. Now, of course, you need a low-pass filter here. So here you will have your resistor, capacitor, RC, time constant, and Bob's your uncle. What happens if V out is not in phase with V1? Now here, as you see, V out has the same phase of V1.
Yes.
But has some phase difference, okay? Let's say that it has this phase difference, okay? Now,
draw some lines there, yeah.
Yeah, I should make it a better drawing because...
No, that was good. That's good.
Now it's not exactly
90
degrees, okay? So I should probably redraw. Now, I should make it precise because otherwise the concept...
Yeah, the concept will be distorted.
Yes. So let's say that now we have still the same VC, which is setting the phase 0, which is corresponding to V1.
Yeah.
Okay. Then
we have 1 and zeros.
Okay. Now, we don't have a sine wave like this, but sine wave like this, okay? Now, we have a phase difference, which is pi half. This is V out, okay? And in this portion of time here, where V out is equal, V prime is equal to V out, we get this voltage, and we get it exactly in the output.
Mm-hmm.
And in this portion,
yes. Now it's negative.
it's negative, but we have to flip it, okay?
Yeah.
So this is positive, becomes negative. This is negative, becomes positive. Okay? And
Opposite.
and so on. And it continues like that, okay? Now, the average that you get after your low-pass filter is going to be 0, okay? So if you take the average of this V prime, okay, this is going to be 0 because this positive part gets cancelled by this one.
Oh, it becomes 0. Oh, if you put this through an LPF, yeah, yes.
If you have a low-pass filter here, you get the average, so this is cancelling this, and so on.
Oh, so that's how the DC value corresponds to a phase shift.
The DC value corresponds to the phase shift, but also to amplitude.
Okay.
Because now we have an output voltage that, let's say that we are in the middle. Okay, so these are the two extreme cases: purely imaginary and purely real. In the middle, you will have this area maybe bigger than this one. If, for instance, you have something like that, okay? So if you have not pi half phase shift, but slightly less. So in this case, this area is smaller than this area.
Yes.
So
the DC value will be a little
will
bit
be
higher.
little, but non-zero, okay?
Yeah.
So it turns out that the output voltage is proportional to the cosine, so the, let's say, average of V prime is proportional to V out, and when I say V out, I say the amplitude, okay, times cosine of phi, okay? You can prove it mathematically, it's not important.
So V out...
Why V out? Because just think about that.
Well, yeah, that's the maximum amplitude of the output.
Yes. Just imagine the first case when it was in phase, when the phase was 0, okay?
Oh, so then you can just divide it by V out and you can get arc cosine and then...
Oh, actually, in this case you don't need it because you need the real part of the... you don't want to measure the phase, you want to measure the real part of the voltage, right?
Ooh,
wait a second.
Okay.
First, let's
not jump.
The first case, when you have phase 0, you got like this. And you got this average value, okay? Now, what if the voltage gets bigger?
The average will just increase.
Okay? Okay. So, of course, bigger voltage, bigger average value. So, it does depend on the amplitude of the voltage that you feed to this synchronous demodulator.
But it wouldn't be V out. Wouldn't it be V out RMS? Because if you put it in absolute, that means it's your peak. And it wouldn't be your peak.
No, in this case, it's the... This will be the rectified mean value, by definition, not the RMS. Careful.
Yeah, excuse me. Rectified, the mean value, not...
The rectified mean value, so it's the value of the rectified sine wave, not the RMS. In this case, it's not connected to RMS. This is quite important because then if you have different waveforms, you have different considerations you have to take. But if you have a sine wave, then you know which is the ratio and so on. Now, V out. So I was saying that this is V out and V prime. So the average of V prime depends both on the amplitude of V out that you feed to the flipper, okay? And of the cosine of V out with respect of VC. Okay, so VC is what we use to control it. So it gets bigger if you get a bigger V out. It gets smaller if you get a smaller V out, but it gets smaller also if the phase goes to 0 or increases, and then you get a smaller cosine, okay? But what is this if not the real part? This is the real part of the...
Oh, okay, I'm going to guess the imaginary part. Is that what you want to know?
No, I'm saying this is the
real part.
It was just a rhetorical question.
Oh, excuse me.
What is this if not the real part? So of V out. So
okay.
If you take V out and you multiply time its cosine,
yeah.
Then what you get is the real part. So if you have a V out which is here.
Oh yeah, and that's just your angle.
This is your real.
Yeah, oh yeah, of course.
So this is V out cos phi, okay?
Yes.
It's the real part, okay. So if you want to measure the real part of a vector, of a voltage, real part with respect of V1, which gives us our control voltage, then just put the V out to this voltage to the flipper, make it flip with the same frequency of the voltage you want to, of the frequency that you want to measure.
Voltage.
Of the input voltage of the operation amplifier, of the inverting amplifier, and then you have a low-pass filter which gives you the average value. What is the advantage of this circuit is that it selects only this frequency, okay? So well, not entirely because, okay, I don't know if I want to enter into the frequency of these things because...
Yeah, it's a whole other thing.
Maybe it's too complicated. But basically here I'm multiplying a sine wave times a square wave, okay? So only, you know that when you multiply two frequencies with two sines with different frequencies, you get the sum and the difference of the frequency, okay? So basically the output will have some value at, the output V prime will have an average value which is given by all the combinations of this frequency with the frequency of the square wave. The square wave have all the odd harmonics, the first, third, fifth, and so on. Remember?
Briefly.
Okay. So let's say that here you have first harmonic, okay? This is the frequency. And here you have first, third, okay, maybe I have to do it here.
And then the sinusoids would have the even harmonics?
No. If you have only sinusoid, you have only one frequency.
No, but if you have two sinusoids...
Hey, wait.
Sorry,
let's say that you have here a signal. It's a pure sine, okay? So you have first harmonic and that's it.
Yes.
Then here you have a square wave. So you have the first, the third, which is 1/3 of the height of the amplitude, the fifth, the seventh, the ninth, and so on, okay? When you multiply 1 and 1, when you multiply these two signals, you get 1 and 1 give you 0 and 2, okay?
Wait, what?
Yes.
So you multiplied 1 and 1, and how did you get 0?
If you multiply a sine times a sine, you get 0 and 2. I mean, if you multiply 50 Hz and 50 Hz, two sines, 50 Hz and 50 Hz, what do you obtain? Let's do it.
Okay.
let's say that you have here you have two 50 Hertz, okay? Now, could you please draw V1 times V2?
Oh.
Let's continue there.
This is a trig identity.
Don't go into trigonometry. It's simpler because then you will forget. No. This is not assigned to W. It's the same. It's the same frequency. 50 Hertz and 50 Hertz.
I would just say the amplitude would increase.
First of all, put down the points that you know for sure.
Okay, this will be 0. This would be 0. This would be 0.
Okay.
And this would be 0.
Fine. So just put down, well, these points. Then put down these points. V1 times V2.
1 times 1 would be 1.
Okay, let's say that. That's the amplitude V1 times V2. This point times this point. Very well. Okay, now connect the dots. No. Shape is not really like that. Much better. Okay, so much better. Why? Because here, in fact, if you watch, you have something which appears a line. If you multiply two lines, it's basically close to 0 sign is almost like a line, okay? So line times line gives a parabol. So that's why here it just grows like that, okay? So what is the frequency of this?
It's omega. It's the same frequency.
Same frequency of this?
Well, at the peaks, yes, but I would
No, there is not the frequency at the peaks.
Well, because here
I will erase this part of the period.
Here the distance between the peaks are the same, but here the distance is not the same.
Okay. Frequency by definition is
how many periods a second?
How many times it repeats equal to itself in a given time, so in 1 second, for instance. So here, what is the period here? Let's say that is 20 milliseconds.
It's half.
The period is half now.
It's half.
So now the period is 10 milliseconds. You see, because it repeats.
It got rectified.
Huh?
It got rectified.
No, it's not rectified.
Well, because like
rectified, it would be like this.
Okay, not the waveform, but it's no longer
the sign.
Yeah.
Okay. Yeah. It's not rectified. It is squared.
Okay.
Because you multiply 1 times 2.
Yeah.
Like if you have 1 volt times 1 volt, it's like squared, okay?
Yes.
Nevertheless. So the frequency is double here. So 50 Hertz times 50 Hertz, 100 Hertz. Because there is a component of 100 Hertz. But that's not the only component. There is also a DC component, which was not present here, nor here. Correct?
Mm-hmm, yes.
Now we have a DC component. We have a 100 Hertz component, and we have a DC component, correct? Now we have a DC value that we didn't have before. DC component, what's the frequency of DC?
0.
0. And here we go. So if you multiply 50 Hz times 50 Hz, you get 100 Hz and 0, okay? And you do it for everything. So if you have now 1, the first harmonic, and the third, you will have 2 and 4, okay? 2 and 4. 1 and 9. You have to make all the combinations, okay? 1 and 9. It will be 10 and 8. The sum and the difference. Correct? Confused? Every time you multiply two frequencies, you have in the output the sum, a frequency component corresponding to the sum of the frequencies, and the frequency component corresponding to the difference of the frequencies.
Huh. And okay, so then the sum corresponds to the new what? Because here the difference corresponded to the DC value, and the sum corresponded to the new frequency.
See? And here all frequencies with a different frequency. Like there will be like 10th. It means that if you have the 10th harmonic, it means that in one period it will repeat 10 times.
Oh, okay.
This is the 10th harmonic,
yes.
okay?
Yes, yes.
Or not here, but here. Here will be 10 harmonic.
Yes.
If it will be the fourth period, it will be like 4 times, okay? The only time you get a DC component is when you get the frequency here matching the frequency in the signal, okay? Because then you have 1, in this case 1 minus 1, 0, okay? So in your circuit, when you have this flipper of polarity, and then you put a low-pass filter, what you do is to select the DC component, or at least low frequency, low enough frequency, okay?
Okay.
Which means that you select from the signal only the frequency which is matching this the frequencies in the rectifier frequency, okay? So if there are frequencies which are not contained here, you don't select them. They will have some output here, there will be some shit here, but they will not have DC component. So it will be noise, go away, okay? So the ideal would be to multiply times a sign, okay? The best thing to do is not to use this polarity switcher.
Okay.
Theoretically, the best would be to take your voltage here and to multiply times a sine wave, okay?
Okay.
So if you are very rich, what you can do, so instead of having your polarity switcher, so this is the output voltage of your operation amplifier. This is V prime, and then we have low pass filter. Instead of using this circuit, and this is the control voltage, you can take V out and multiply it times V1, or the input voltage of the operation amplifier, okay? Which means that you have V out, you have V1, and then you have two sine waves, okay? So it means that if they are in phase, in case it's purely real impedance, you will have, as we saw, something like that. You take the average value, and that's it. In this case, you have only the first harmonic here, the first harmonic here, and then you have the DC value and the second harmonic. Okay. Now, in this case, if the signal contains some bad frequency, okay, some disturbance whatsoever, you don't have any problem because they will never end up in zero, okay? They will be multiplied, and the output will contain frequencies which will be here, 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 according to the sum and difference with 1, but they will never be to 0 because the only case you have something in 0 is when you have 1 minus 1, okay? Is this clear?
Mm-hmm.
Okay.
So actually, can you repeat it?
Okay. Let's say that you have here 50 Hertz, okay? And here you have, no, it's a bad example because 50 Hertz is the typical disturbance.
Oh, because it's in the wall.
If you are in a country like this, if you are in Japan, you have 60. Depends on which part of Japan you are.
It's so strange they have different frequencies on the grid.
Oh, yes, but the point is that they electrify the countries without thinking that sooner or later they have to join. You know?
Really?
Yeah, because in the south, they imported generators from United States and from General Electric, which were 60 Hertz. Then in the north, they imported generators from Germany, which had 50 Hertz. And then when they arrive in the middle, say, oh, what the hell, we have to join, we don't know how to. Now there are some DC link between the two networks.
Wow.
Otherwise, they are they were disconnected the networks. It's a historical reason. Nevertheless. So let's.
Okay.
So we have 1 kilohertz and 1 kilohertz. So the output will be 0 and 2 kilohertz, okay?
And 0.
And 0 kilohertz. Then let's say that you have a disturbance at 5 kilohertz, okay? Whatever. It's another frequency which is not supposed to be there. It's just some picking up from some electromagnetic fields in the net. I don't know, whatever. So, some disturbance.
The trams.
Whatever. Then, when you multiply this 5 kilohertz here, so this signal will have also some 5 disturbance, okay? We'll have some 5 kilohertz added to that. But then you multiply times 1 kilohertz. So what do you get? 4 and 6, okay? So you have 4 kilohertz and 6 kilohertz.
Yeah, okay.
So here, of course, there will be, again, some disturbance. But it will not affect the DC value. The DC value will be given only by 1 kilohertz by 1 kilohertz. So all this that you have here is not influencing the output.
Yes.
Because you take at the output only the DC value as your output of the system.
Well, as your reference between real and imaginary.
Not between real and imaginary, but in this case I'm measuring the real part, for instance. Okay?
But if the DC is 0, it's purely imaginary.
No, if you want to measure the imaginary, you do another way. You flip the reference by 90 degrees, or pi half, okay?
Couldn't you just take... Okay, so if
you want to measure the imaginary part, simply you have a phase shift.
If your real part is V out, right? That means cosine phi is 1, which means it's not imaginary at all. But now, if cosine increases a bit, you know there's an imaginary component, so you can just take the
How do you know that there is an imaginary component?
Because the average value is not... the average value is not equal to the magnitude of V out. So that means that cosine has a component.
Okay, but you don't know which is the amplitude of V out. That's the point. Here you have an output which is V out times the cosine. You might say, okay, let's say that we see 0 there. Okay, here I see the DC value is 0 volts. Does it mean that it's purely imaginary part? No, because it could be because it's imaginary, or because here there is 0 volts.
Okay.
There are two possible ways. So you don't know it. So the only way you have to do is, if you want to the real part of the voltage, use this circuit. If you want the imaginary part, you have to move the reference by 90 degrees.
And then you see
you see sine.
And then you see the
out.
So then the DC value will correspond to what when it's phase shifted by 90 degrees?
It will correspond to the imaginary part of the voltage.
Okay. So if you take the DC imaginary, what's the relationship between DC imaginary and DC average or DC real?
The circuit by itself, it measures always the real part, okay? This circuit by itself measures only the real part.
Okay.
So it will always measure, let's call it
so
here.
So you get the same DC value.
Star.
No, sorry, just carry on.
V star is always V out times cosine of phi, okay?
Yes.
Where phi is the phase between V out and the control voltage.
Yes.
Period. Then, if you shift the VC by a phase of 90 degrees, okay, then you will have the cosine of an angle shifted by 90 degrees. Okay, but if you shift the angle by 90 degrees, the cosine becomes a sine.
Yeah.
Okay? So the circuit by itself measures always the real part. But if you rotate the reference system by 90 degrees, what is real becomes imaginary and vice versa. Okay? So
yeah, exactly.
It will be like phi prime, which corresponds to sine phi. Okay? But what I was saying here is that all this disturbance will not play any role in the DC value, because in the DC value you get only
the first harmonic.
The first harmonic, because it's the only case when you have a difference of the two frequencies which gives you 0.
Yes,
okay?
Yes.
So
unless there's also noise in the input. So if Vn had noise,
of course,
then there would be something else. Yeah.
If there's here, then you will. If you have by accident 5 kilohertz here, then you will have also 0, 0. So, but if you have a very nice pure sine wave at the input, this method allows you to erase all the disturbances. Okay. This is one. The point is that multiplying two signals is not so easy. If you watch all the analog multipliers, the noise is quite large. Okay. So theoretically, this is a nice system, but then you should always go and check in the reality which are the numbers in terms of noise, because sometimes it's just better to use the flipping system when you go down to the numbers of the noise. Okay. In theory, it's better. In reality, very often it's just better to use the flipping system.
Okay, can I show you, demonstrate a way that I think is the same way that chip does it?
Okay.
Okay. So
no, use this.
Okay. So how do you measure, let's say, resistance, inductance, or capacitance in any way you want, right? So let's say they ask me that, right? So on eBay, you can buy these really cheap multifunction meters, and it's not just for capacitors, it's not just for reactive components, it's also for semiconductors. So you can measure diodes, transistors, etc., right? So, but I don't really know how it does it with semiconductors, but I think I remember how to describe how they measure the reactive components.
Yep.
Okay, so firstly, let's describe the reactance of inductors and capacitors. So XC is equal to 1 over 2 pi FC. And XL is equal to 2 pi FL, okay? And you can think of reactance as resistance. They both have ohms, right? And it's not a complex value, it's a scalar value, right? Okay. So now let's imagine we just have a simple voltage divider where we have R, which is known, and then we have some component which we don't know. So that's the component that we're going to put onto the connector, right? And then we have V out, okay? And then this is Vn, okay? And you can describe it simply as V out is equal to, let's call this R question mark. So R question mark divided by R1 plus R question mark times V out, right? Okay.
No, times...
excuse me, V in, pardon me. So now, you can get a simple like Arduino, right? That's what they use for these really cheap multi-testers, where you'll have the microcontroller. You'll have an output with a PWM. This will go in to your known resistance. This will go to some connector. This will go to ground. The microcontroller is also ground. And this here will go into the ADC of the microcontroller. So you can modulate a frequency, whatever it is, 1 kilohertz, 10 kilohertz. You can read the voltage of it. And since you know R and you know F, you can solve for what L or C would be in that equation.
There are several problems with this approach.
But it works, right?
No.
What do you mean?
But, it works. It works. Everything works. It depends to which extent it works.
You won't get like. You would just get the inductance. You wouldn't get like the real and imaginary part.
Okay. So the point is that first of all you have to understand. Okay, what you get. What do you get here? You get
a voltage.
A voltage, yeah, but then you make some demodulation internally, or because then the voltage will change if you had PWM, right? Okay.
Probably a low pass on the output or the input of the.
So you can make you can make a digital demodulation. Okay, so which is what is done in that chip I was talking about. Let's see if meanwhile my colleague has written me the name. Okay, so yes, in some terms you can use it to if you are able to internally make a demodulation of this voltage, okay? I don't know if the microcontroller you're talking about is able to be fast enough to do it. I don't see any reason why you should generate a PWM then. Just generate a sine.
Okay.
Okay. The problem is then, okay, when I didn't understand what you mean if you use this PWM, if you want to change the frequency or not, or if you want a constant frequency.
Probably you would have a range of frequencies and then you get the average.
Because the point is that here you will not have only a reactance, you will have a resistance, okay? So you must be able to, if you want, you must be able to distinguish between these two components.
Maybe
Okay.
this device.
So this is
assumes
not.
it's 0.
This is not technically true, because you will have this also some resistance. So this is kind of tricky, because it gives me the feeling that you believe that if you put the impedance, there is only impedance, but there is not. There is also a resistance.
A real part.
And so you must be able to distinguish. And this is not really the case, because you have to take the real and imaginary part of the voltage. So we are back to the same problem of before. One of the problems, you say, okay, I use frequency where I go up and I consider the resistance negligible. I don't know. If I use a frequency where the resistance becomes negligible compared to the reactance, I can kind of forget about that, which is one approach. But, okay, the reason why I said it works to some extent is because it depends on how precise you want to be. If you want to be not very precise, everything is okay. So you can say, okay, I get to the point, I go up to a frequency where the resistance becomes negligible, and who cares if I have some resistance there, and so on. But you should remember that the resistance changes with frequency as well. You should remember that the impedance changes with frequency itself. If you have an impedance which is based on ferromagnetic material, so you have a coil, some ferromagnetic material, the properties of the ferromagnetic material change according to the frequency. Okay. So also L depends on the frequency. So you can say, okay, I will go up to a frequency. Yeah, but what if I want to measure the impedance at low frequency? You cannot just tell me go at high frequency, okay?
Yes, yeah, you can't, if you want to know at 10 hertz, you can't measure it at 1 kilohertz.
So
but that's usually why inductors will tell you this is 1 Henry at 1 kilohertz.
Exactly, so it's the frequency.
The inductance is not constant.
Exactly. So the actual equation would be this one.
Yeah, like you wrote earlier.
V out is equal to, so it's Z question mark divided by Z question mark plus R times V in, okay? Which is in fact what we did before, because we generated some current when we had the operation amplifier like that. V in, and this is the current. We call it R2, I don't remember, whatever. And this is what our Z question mark, V out. What we did with this circuit was to generate a current, which is given by V1 divided by R2, and feed the current to the unknown impedance, and then measure a voltage which is given by this impedance times unknown current.
And that op amp is just
which is the same thing that we are doing here. You generate a current which goes to the impedance, and then you read the voltage on the impedance. What's the difference? Again, why this circuit is better than that one to this extent? Is here the current does not depend on the impedance that you want to measure. Here the current, I, will be V in divided by R2, period. Okay? And then this current cannot enter in the operation amplifier, so it goes through the feedback resistor. And it doesn't depend on the feedback resistor itself. So it doesn't depend on the measurement, on the quantity that you want to measure. Here it does. Okay? So here the current which flows through the impedance that you want to measure depends by the impedance itself. which is bad. Why? Again, if you want to measure an impedance and you have a ferromagnetic core,
Yeah.
you remember, if you measure in this range of current, so this is H, which corresponds to how much current you put inside, and this is B, which corresponds to the flux, okay? So flux is inductance times I. So if you are in the linear range, no problem. But nothing is actually linear in a ferromagnetic material. So if you use a different current, then you have a flux which is not linearly increasing with that, okay? So again, not only depends on the frequency, but depends also on the current that you want to measure. In fact, when you measure with some LCR bridge and you change the current, you see that the resistance, and if you go to the extremes of the BH loop, you see that the impedance changes also with the current, okay? Of course, if you have a relationship like that, it's not a problem, okay? But if you have a BH loop which is far from being linear, then you have a measurement which depends on the current that you inject, which is not so nice because you want the current to be always the same to have a reference. To avoid the distortion, just think about that. You have an impedance which changes, then the current changes, and then you have an output voltage which changes, not only because of the impedance, but because of the current, which makes the impedance be fed by a different current. It's all complicated, okay?
Yeah.
So always, as much as possible, when you're talking about sensors, and the output will depend on the current that you inject, just try to keep the current that you feed, the test current that you feed to the impedance, to the resistance, to whatever you want to feed, to be independent on what you want to measure.
Okay.
Okay? So this is something that I would always recommend. And unfortunately, this is not true. Unless, as usual, what you do is to have this resistance much bigger than this one, so that the current will depend mostly on the resistance, but then the voltage will be small. Okay?
You need a precise ADC.
Exactly, you need a precise ADC, which is not typical what you have in
an Arduino.
an Arduino. Or if you want to have it precise, then it's not fast enough, and all these sort of jets, okay? But definitely you can do it digitally. That circuit I was talking about, let's see, it's, okay, it's AD 5933. It's from Analog Devices.
Yeah, that's not a Texas Instruments number.
And basically, let me check. There's some nice board, evaluation board. I'm not making advertisement. It's just it's just a case which happens to me.
It's what you like.
No. Actually, I don't like because I typically do these things by myself. But this is quite. Let's see how much it costs. In fact,
The evaluation board or the chip?
No, the chip itself, the evaluation board. You can do it by yourself. They don't state the price. At least I cannot find it.
Not on DigiKey? Or?
But they have up to 100 kilohertz. Then they have inside a generator of sine wave which has a resolution of 27 bits. Okay.
Jeez.
So they have this generator basically.
27, that's an odd number.
Why?
No, usually it goes up in even.
Well, that's an odd number, yes. I believe that the odd was not referred to the number itself, but odd like strange.
No.
That's an odd number.
No, like, well, I guess it is also odd because it is odd.
That's strange. Maybe that's the reason why they call it odd. so they have a digital to analog converter, which is feeding an operation amplifier. And here they have some resistor they can tune to give some different amplitude. Then you get out of your chip, then you get, so maybe I will erase. Here you put your Z impedance, and then you go back. You have again here some, you use this, you have a circuit like this, blah, blah. It's not important to do this. Okay, and here, then you amplify with some gain. And then, oh well, there's some low pass filter. And then inside, there is a 12-bit analog to digital converter, okay? Which is taking the same frequency from the source of frequency. There is an oscillator here, from which fits the DAC, okay? So basically, the oscillator creates a sine wave step by step. Okay, so in fact, what it does is to make some step like that, then you smooth it out with some filter. Okay, so and you know after some time you finish a period. The same frequency is fed this to synchronously sample the voltage out of the bridge. And then there is some microcontroller inside, or some DSP, actually, how they probably they call it. No, this, yeah, they have some digital Fourier transform. They have some 1024 digital Fourier transform, which basically calculate the Fourier transform of the voltage output of the bridge. Okay, in this case it's 4 impedances, so it's 4 capacitances. So in the feedback we have the resistance, and in the input we have the unknown. Okay, otherwise you can just flip it. Okay, so in the feedback you put your unknown, and in the input you put the resistance. And here, basically, you have your waveform that you sample. Okay, this is your V out that you get here, and simply you digitize it. You take the samples, and then you can calculate the discrete Fourier transform, so that you get the spectrum, and you get the component, your first harmonic, which will be given in amplitude and phase. And then if you have the amplitude and phase, you can calculate the real and imaginary part. Because the Fourier transform gives you both the amplitude and the phase of each frequency component of the signal, okay? So you have the frequency, you have the amplitude, you have the phase, you can recalculate the component of the impedance, of the voltage, so the real and imaginary part. Okay. And then, of course, there is some interface, I2C interface, which to get out from the... So what you get here is everything is done inside. You have the oscillator, you have the DSC, and so on. Then you send some parameters to change probably the frequency, I don't know, whatever. I don't know if you can change the amplitude again. I didn't study the datasheet very well, but then you connect these points here at the output, and you get inside what you get, okay? So, of course, you can do it also this way. Digitally, if your system is precise enough, it's synchronized well enough, then you don't need to make any flip and so on. You just you calculate the digital Fourier transform and pops your uncle you have digitally you have done the same thing that otherwise you would do by multiplying and so on.
All on a chip.
Exactly. So this is the problem. This is how you can do it in such a way that you can always measure continuously the impedance, okay? Or the capacitance if you just flip. So just for the record, if you want to measure the capacitance instead of the impedance, it's the very same thing. You simply have to flip the rows of the resistance and the capacitance. So if you want to measure capacitance, then you put your capacitance here, your resistance here, V input, V output, and you recalculate everything, okay? The reason why the capacitance is now in the, you know why? Can you try to guess?
Because the feedback currents on the resistor wouldn't pass through the capacitor if it was.
It's AC, so
okay,
it doesn't matter. Just watch it. How do you define XC and XL?
It's the inverse, or it's complementary.
It's one up, one down.
Yeah.
Numerator, denominator.
Okay, so it will just make the equation easier?
Yes, in some sort of sense, yes. Because
you won't have
you flip the role of the unknown and unknown of the known and unknown,
yes,
so that you have the output voltage always proportional to the unknown. Okay, so if the unknown goes downstairs in the fraction, then you flip it up by using the fact that you have 1 over 2 pi f c. Okay, so it's always in the same line with the so there is proportionality between V out and the unknown. Okay, you can write down the equation and you see that in this case again V out is proportional to C, and in the previous case it was proportional to L. Okay, so if you put C here, now it would be proportional to 1 over C. Okay, so it's not good anymore because we want proportionality. We want linearity between the output. Oh, sorry, bad mistake. Between the output and what you want to measure. Okay, fine. It's quite interesting that. But you want to measure only in impedance, right? You don't care about capacitance. Now, because the problem of capacitance is that they always have these parasitic capacitances and so on. So one thing you can do is to shield your capacitance in a shielding. So there will be some. So just imagine that you have your capacitance, and you shield it with some conductive material. Okay. Whatever is conductive. So what you develop then is a sort of parasitic capacitances between the capacitor, each electrode of the capacitance and the shield, okay? So which means that here you will have a shield and you have some parasitic capacitance to the shield, okay? The problem is that if you use this circuit this way, what you measure is your capacitance C plus parasitic, okay? So you measure the parallel of Cx and the series of Cp and Cp, okay? Which is not good because you want to measure only Cx. But what you can do is to put this to ground so that this capacitance will be shorted by the virtual short circuit here because there will be 0 volts here. This capacitance is not creating any problem because it will be in parallel with the virtual, with the ideal source of voltage, if it's ideal, which means that it's just an extra load that you give to this voltage source, but it doesn't affect the current here, okay? Because if you have a ideal source of voltage here, then you have an extra capacitance here, fine. It will feed the current here, but it will not change the current which goes into this capacitance. It will just an extra current that will generate. Of course, if you have here some internal impedance, of course, it will affect the voltage at this point if you draw more current. But if you don't have this, it won't be affected. You just have the double, these two currents together getting out from the source of voltage without the voltage to change, okay? If there is no impedance here. So now, just so be careful, because if you use one of those chips, like the one that I've shown before from Analog Devices, you might want to remember this fact so that you know that maybe you can find the ground in your circuit, in the chip, so, and you connect the ground to this point to avoid this measurement of the parasitic capacitance, okay? Fine. Now, this is a method that you can use to measure these things quite effectively if, for instance, the inductance of the capacitance change in time, and you want an output voltage which can be measured constantly by analog to digital converter, for instance, and which is proportional to the capacitance or the inductance, okay? Fine, it works, but there are some sources of uncertainty, okay? Like, what source of uncertainty you see here?
The components themselves, and the op-amp, and the device you'll be measuring the V out with.
Well, the op-amp, yes. Then what?
The uncertainties of the components. So, well, actually, C is unknown, but R will have some uncertainty in it. Possibly the voltage generator could also have some uncertainty. And yeah.
The voltage, of course, it has some uncertainty. You think that it's 1 volt, but is it really 1 volt?
0.99.
Then there will be, I don't know, it depends if you have the modulator, you have the noise of the demodulator. If you do it digitally, you will have other source of uncertainty and all these sort of jets, okay? So this is good because if you want to measure an impedance at this continuously changing, you have to transform it into a voltage, because then you know how to measure voltage continuously, okay? So you need to transform an impedance, reactance, or a capacitance, or an impedance or inductance or capacitance to a voltage. Okay, so you have to convert.
Yeah, some value to voltage.
To voltage.
Yes.
This could be inductance, capacitance, whatsoever. Okay.
Or
combination of them and so on. And then you measure the voltage. Fine. But of course, there are all these sources of uncertainty. So there are other methods to measure the impedances, which are sort of more precise, which you do not have these sources of uncertainty. And but they are okay. Maybe it's not precise. They are slow. Okay. So we will see some of these circuits now. Okay. So let's erase everything. Okay. So this is a circuit, for instance, that we can use. There are plenty of bridges, okay, really, for any type of thing that you want to measure. This is, for instance, if you want to measure a capacitance. So this is our unknown. This is a constant capacitor. This is a constant resistor. And here we have a variable capacitor and resistor. We have a source of AC voltage. And what we do is we change C1 and R1 until the voltage is 0, okay?
Yeah.
If that voltage is 0, it means that the voltage between this point and this point is the same, okay? So let's say that this is VA and this is VB, okay? If we know that here the voltage is 0, it means that VA is equal to VB, okay? So we know that VA is equal to this impedance, okay? So it's 1 over J omega C3 divided the parallel of 1 over J omega C1 and R1, okay? Plus 1 over J omega C3, okay? Because we have a voltage divided between this impedance, which is 1 over J omega C3, and the impedance of this and the impedance of this. So
where's R2?
There's no R2. We are talking about this part. C1,
Oh,
R1,
yes,
C3.
yes, yeah.
Okay, sorry. Okay, maybe it's better if you do it like symbolically. Let's put it this way. Here we have the impedance Z3 divided impedance Z1 plus impedance Z3. Then you know that the impedance Z1 is 1 over J omega C3, and the impedance Z1 is the parallel of R1 and J omega, 1 over J omega C3, C1, times Vs, okay? Vb will be, again, the voltage divider of this impedance, let's say Z4, divided by Z2 plus Z4, okay? So this is a general solution which applies for any type of bridge. Then, in this bridge, we have this element, so we can substitute it and get the equation. We solve it. If you solve the equation, you find out that R4 is equal to R2 times C1 divided by C3, and C4 is equal to C3 R1 divided by R3, okay? So what you do is to adjust C1 and R1 until you get to a 0 voltage, and then you know the value of R4 and R4 and C4 according to these equations, okay? What is the advantage here? Can you spot it?
The temperature difference will not affect.
Not even go to temperature. Which were the problems in the previous circuit?
Uncertainties, I think, cancel out here.
Uncertainty of what?
Of the capacitors, of the components, let's say.
Not really the components. Think about before. What changed if you change the input voltage of the bridge? Of the operation amplifier. Remember, we have the circuit.
Yeah.
And we have this, blah, blah, blah. V out, V in. V output depends on V in, okay?
Yes.
You get double V in, you get double V out, okay?
Here's not the case.
Here we don't care. Because as long as the bridge is balanced, let's say this bridge is balanced, here there could be 1 volt, 10 volts, 1000 volts. If the bridge is balanced, the voltage here is going to be 0, okay? So we really don't care about the voltage source. This could change in time, could be noisy, could give all this sort of crap.
As long as the voltage is 0?
As long as the output, the measure voltage is 0 here, it means the bridge is balanced, and we don't care, okay? We just need some voltage to feed the circuit. Then if it's noisy, we don't care. Second point, here we don't really measure the voltage. We just measure that it's 0. If that voltmeter is not good, like if it has a characteristic, like the voltage that you measure and the voltage of the actual voltage, let's say, actual voltage of that and the voltage that you measure with this voltmeter, okay? It's something like this, bad characteristic. You don't care. You can have a bad voltmeter. The only thing you care is that when it's zero, it's really zero. If you don't have any offset, then the characteristic could be all that possible. It could be as bad as possible, as long as it's in zero. Maybe here's not a good wise. It's not. No, it's not wise to have like this, because then it could, in feedback system, it could stuck in a point where. Okay. So it should be monotonic at least. Okay. You don't need a voltmeter which is linear, perfect, all that sort of jazz. We just need that it doesn't have an offset, okay? So if you're able to make a voltmeter which has no offset, you are all set.
Okay.
So if you watch here, it depends only on the components of the bridge. But to some extent, you can have these components very good. You can have some components which have very high precision. You calibrate them, and you put them in the circuit. This also you can have some precisely tunable resistor and capacitor, and you're fine. So there's really not a big deal in creating this circuit. The point is that you cannot do something very fast, because every time you change the impedance that you want to measure, you have to change every time these things. Now, if you do it manually, the speed of measurement is the speed that you have, you can do it automatically. So what you can do is to measure here the voltage, and then an automatic system can adjust this capacitor and resistor. But again, it's not as fast as measuring a voltage out of operation amplifier and then recalculate the impedance. So you can use this system if you want some very precise measurement where you cut away all sort of uncertainty, and you're left with this uncertainty, which depends only on the components, okay? And you can have some good components. There are other circuits. For instance, I will show you this. So, what you can do is, in fact, to use this circuit where you have an autotransformer which feeds this unknown impedance, resistance and capacitance, so that some current will flow here, okay? So let's say that we have a voltage here, and this is current which flows here. It flows here, and it will generate a current on the other side of the transformer, and it will be measured by this ammeter, okay? Then you have this capacitance and this resistance, which will be exposed, or they will be subject to a different voltage, okay? Which is given by this voltage applied to this capacitor, or if you let me find another color, to this voltage applied to this resistance, okay? So you change here the position of the tap of the autotransformer, and you give more or less voltage to the capacitor and to resistance. This will generate some current in the capacitor and some current to the resistance, okay? So here you will have not on the other side of the transformer, you will have the current given by the unknown impedance, okay? Which will be a complex current. It will have a real and imaginary part, because here you have a resistance and then a capacitance, okay? So generally speaking, you have, again, a real and imaginary part, okay? Then here, you have separately the real and the imaginary part, okay? So what you do is to, again, check when the emitter gives 0. When the emitter gives 0, it means that this real and imaginary part are cancelling the real and imaginary part of the unknown impedance. So you don't know which is the current here. It will have some real imaginary part. So if you want to null this current, you need a real and imaginary component of the current. So you need some capacitance and some resistance. Okay? So what you do in this case is not changing the capacitance or the resistance. In the previous circuit, we were changing the value of the capacitance and the resistance. Now we say, okay, let's say that we have some very beautiful, very well calibrated capacitance and resistance. They are not tunable, so we cannot change their value, but we can change the voltage on them. Okay? So in this case, we don't change the value of the components of the capacitance and resistance, but we change the voltage we apply to them in order to have a different current. Okay? And so what we do is we change here the voltage that we apply on the capacitance and the resistance in order to have the current in the secondary of the transformer which cancel completely. Are you missing something?
No, carry on, please.
That are canceling the unknown current, okay? So what you're doing here is to check again.
And that voltage is changed by tuning that point.
They're changing the tap here in the autotransformer. Okay. And that's the important part because here you have an X, I think is this one, and NC is this one, and then we have an R. So these are the ratio of the numbers.
Yes.
Again, you write down to all the equations, you solve them, it's just mathematics. So this is the ratio of the turns on the transformer. These are the numbers of which are giving the voltage on the unknown resistance, known impedance, and the unknown and the known capacitance and the resistance. So here you have an how we call it, an R. So here we take some number of taps that are proportional to the voltage to fit the resistance, and we call it C to fit the capacitance. And then, of course, we have a fixed number, NC, okay, which are feeding the unknown impedance. So you change NC and NR to calculate until you get 0 current in the secondary. If there is 0 current in the secondary, it means that in this transformer you have the currents in this section, which cancel each other out, and therefore we know that the sum of the current is 0. Then you make your equation, you end up with this final equation.
The impedance has become equal.
So in this case, we don't change C and R anymore, but we change the current through them. What is the advantage here is that the source of uncertainty, the actual, almost the only source of uncertainty, is this capacitance or this resistance, depends on what you want to measure. If you want to measure this capacitance here, you have the number of turns, but the number of turns is very well defined.
Yeah.
If I have 100 or 101, it's 101. It cannot be like 99.7, okay, turns. It's very well defined. Then the main source of uncertainty is the uncertainty of the reference. So if there's an uncertainty, basically you have it propagates directly to the uncertainty that you want to measure. So basically, if you have a capacitance here, more or less with the same... have you noticed that I flipped out? If you have this capacitance here that you want to measure, how embarrassing. We will not repeat it, of course, we just let it be. Of the same amplitude, more or less, you will have the same number of turns here. So you can actually measure this capacitance and have almost the same uncertainty of your reference, which is good because you have a very good standard with very good uncertainty, very low uncertainty. And you can calibrate this capacitance almost having only this as a source of uncertainty, which is very good, okay? So this is a method if you don't want to add additional sources of uncertainty to your system.
What about the ammeter? Wouldn't that be a bit uncertain?
Again, that's the same problem I said before.
With the zero.
As long as it's zero, it's zero. So in this case, if you don't have any offset in the ammeter, again, of course, there is a problem. So you use an ammeter which measures really zero when there is zero current.
Yes.
Okay? So this is one of the methods that we use if you want to calibrate an impedance when you know that you want to have an uncertainty as similar as possible to the uncertainty of your standard. And if you have a standard, typically you don't have it tunable, not as much, because the fact that you have to tune it introduces some mechanical problems, which make
also a lot more uncertainty.
More uncertainty, okay?
And noise.
So we want, if you have a good standard, typically is constant. Then, of course,
yeah, and also because if you're doing a bunch of measurements, that uncertainty would be in all of them, so it would sort of cancel out, right? It would be like a universal offset. So if you're measuring a bunch
of what?
A bunch of capacitors and resistors. And you're trying to measure them, but you keep everything in the system constant.
You want to... No, in this case, I was just saying if you want... so if you want to characterize a set of production line, okay.
Yeah, then the uncertainty is in all of them, so it sort of balances out.
I think this kind of circuit is used to measure really something if you want one piece to measure. If you want to measure a batch of production, use much simpler and less expensive methods. Anyhow, then of course, if you want an impedance, you have to do the same thing using instead of the capacitance, the impedance. Okay. Again, you will have a current which will have a real and imaginary part. The imaginary part will be in the opposite direction because you have an impedance instead of a capacitance. So you put their impedance and pops your uncle. You do the same thing. Okay. The principle is the same. Again, you see, it depends on what you want to measure. This system is extremely tedious, but extremely precise. So if you go in some laboratory where they make metrology, calibration, all this sort of jets, and they are crazy about going down to the lowest possible uncertainty, they use this kind of... Sorry.
No. Yo. Our sugar levels are low.
They use this kind of circuits because they are very precise and they give you very low uncertainty. If you want some circuit which is used in an industrial production or in an automatic system, whatever, which continuously measure the impedance, then you use the one that I've shown before with the operation amplifier.